everyone, and welcome to CSCI 343 Fundamentals of Data Science. Today, we're going to continue our hit the ground running introduction by talking a little bit about plotting data. So, without any further ado, let's get into our slides. Okay, so as most of you know, I'm kind of a weird computer scientist for a lot of reasons. One of those is that I'm actually more interested in the user of the technology than the technology itself. So specifically, what I do is I use virtual reality to study how people perceive the world around them and perceive 3D relationships and behave in those 3D spaces. Now that's kind of cool. It helps us understand the technology, but it tells us a lot about what's going on in the head of the person using that technology. So when you study sensation, perception, cognition long enough, you study not just its function, but you also study its dysfunction, the times when things sort of break down and weird stuff starts happening in the head. So one interesting dysfunction is called synesthesia. So when we think about how we see the world around us, or rather, not even see, interpret, detect, that's a better word, detect the world around us, we've got a bunch of sensors on us. Our body is bristling with sensors. We feel things in our skin, we feel heat and temperature and pressure. We detect photons, light with these two little cameras inside our head. We have inertial sensors, not too different than what's like in your cell phone, inside of our inner ear that detects our physical movement. And of course, we have the ears themselves that detect sound. We've even got sensors embedded in our muscles and joints that tell us the relative position of our arms and legs as we move around. We are bristling with sensors, collecting raw data, information about our surroundings. And then our brain takes that raw data and tries to turn it into something meaningful. We can call these meaningful things that we're trying to extract from our raw data percepts or perceptions. So what happens when some of that raw sensory information gets funneled into the wrong or some of that sensory information gets funneled into the wrong processor that makes a particular percept? So we end up, say, getting physical sensation crossed over with, say, vision or hearing. So touches start becoming visual sensations or sounds or something like that. That cross-sensory stimulation is called synesthesia. Now, synesthesia is interesting. A common form of synesthesia is number-color crossover. So there are some people who, when they think about numbers, or they read numbers, they actually experience vivid shape and color sensations along with them. And that's really fascinating. Now, this can also be disruptive to life, as a species, we've developed, sensing and detecting and interacting with our surroundings in particular ways. So, you can see this as being, sometimes a disturbing and perhaps unwanted sensory experience. But what if you could harness this sort of sensory crossover at will? Take raw sensory information from one location and perceive it as something else. Say, actually take and turn on and off number vision crossover. Well, essentially, that's what you're doing when you're plotting data. Kind of like with our Battlestar Galactica reference on the first day, if you can capture information, if you can record data of any kind and visualize it, you're essentially enabling yourself to see things that you would not normally be able to see. Essentially taking sensory information from one location and then interpreting it in a completely new and different way. So one might, sort of ask, well, why would we want to do that? If we've got the data, why don't we just look at the data and use that? I mean, we're all smart folks here. We've got a room full of virtual engineers, right? So, you could look at this. And do you see the pattern? This would be where I would do this in the classroom, and someone would say, well, it's a sine wave, and it's getting bigger over time. And you're right. These data represent an oscillating sine wave whose amplitude is increasing over time. Matter of fact, it looks like this. So yeah, you're smart, You can look at this and you can extract data from just the raw numbers itself. So why bother? We know what's going on. Well, the reason that you want to bother is that the human brain is cool. We are excellent at seeing patterns. We can look at visual information and extract patterns very, very quickly. Yeah, sure, you could look at these raw numbers here and figure out the pattern pretty darn quickly, but we also have blind spots. For instance, you probably didn't notice that I changed these raw numbers. This no longer represents the plot, and you didn't notice, most likely. So this is now the data that these numbers represent. And here's the thing, if you were looking at the plot itself and not the raw values, this would have popped out to you immediately. You would not have been fooled by my contrived little experiment here. And that's the power that plotting data gives us. It takes advantage of the human capability to recognize patterns very quickly. Now, plotting data is essential to everyday life. Whether you realize or not, you're plotting data constantly. Now, this could be in the form of you looking at the plot from your fitness watch or your Fitbit or whatever the heck you're using. Or it could be you just looking at memes on the internet. All of these are plots of a particular form or another. And you don't necessarily need sophisticated equipment to do complicated plots. Matter of fact, it's all math. If you have a program that'll let you visualize something mathematical, you have a superpower. For instance, this right here is a 3D renderer written in Excel. Matter of fact, I wrote it. It can be done. Anything where you can visualize things mathematically or visualize mathematical things, do a plot, you can do amazing, amazing things. And the tools don't necessarily have to be terribly sophisticated. Now, granted, do you want to write a 3D renderer in Excel? No. It is a bad idea. It's just a terrible thing. If I wasn't having to make this for something else and realized, well, this is essentially a 3D renderer, I wouldn't have done this because it's a nightmare. You want to use the right tools for the job. Now, the plots we're going to be using in here are pretty straightforward. They're mostly going to be 2D plots, and they're going to have certain characteristics in common. For instance, we're always going to have a horizontal axis, an x-axis, and a vertical axis, a y-axis. Typically, the x-axis is going to be our what are we presenting, the thing, or also sometimes called the category axis. The vertical axis usually represents some sort of quantity. So the how much, or the response, or the amount, our value axis. Now, remember these terms because, they might be on a quiz. So always label your axes as well. I can't tell you how many visualizations I've looked at in classes that I've rejected, or even in papers that I've reviewed, like actual scholarly papers, people forget to label their axes, and the reader doesn't know what the heck you're trying to tell them. So in this class, you absolutely have to label your axes. If you don't, I won't accept your plot. So for every plot, label what your x-axis is and label what your y-axis is. In this example, this is plotting the 25% tax bracket cutoff for the year 2015 and the year 2016. And so as you can see, there's a pretty big difference between those, So our what axis is tax year, our category axis. Our value axis, the thing, the quantity, the amount, the thing that we're plotting, is income along the vertical axis. Now, another property that you need to take into consideration very seriously when plotting data isn't just what your axes are, but also the scale of your axis. Now, that looked like it was such a really big difference between 2015 and 2016. Somebody's messing around with their numbers, But that's not really the case. If we look at it from zero until, $90-ish thousand, we can see that the difference between the cutoff for that tax bracket between 2015 and 2016 was actually really, really small. Matter of fact, less than 0.5% difference. So always make sure that the scale of what you're plotting is communicating the thing that you need to communicate. And this is sort of an ethical thing with your plots as well, You don't want to mislead the person seeing your data. Now, we're going to be talking about, or using rather, certain plots over and over and over again. Now, we're going to use them in different ways. There's three basic plots we're going to be talking about. We're going to be talking about scatter plots, line plots, and bar plots. Now, these plots, there are many other plots out there, but most other plotting methods can sort of be generalized down to a special case of one of these kind of plots. Now, if you're not familiar with matplotlib, that's okay. We're going to go over some examples of that in today's lecture. But if you need more information about using matplotlib, there are some excellent resources on Matplotlib's website. It's actually a really easy tool to use. The examples we're going to go over today are going to give you most of the information you need to sort of hit the ground running and do basic plots. As a matter of fact, it'll give you enough get up and go, so to speak, to do your first assignment in this class. Okay, and with that, let's write some code. Okay, let's do some examples. So through the magic of video editing, it's going to look like this is happening immediately after the previous part of the video, but let's just say it's not. It's been a long and unexpected day. Not necessarily a bad one, not necessarily a good one. So, like I mentioned in class, you can use pretty much any development environment you want in here, just as long as you're the one writing your code. I suspect a lot of you are going to be using Anaconda, because it comes with pretty much all the libraries you're going to need built into it, and has a nice clean editor called Spider. So that's what most people end up using. But I do encourage, especially our CS students, to try working from a terminal. This is actually my preferred method of coding, but then again, I was raised by a wild pack of Unix programmers, so, take from that what you will. So I actually arrange my terminals. I usually use two. Usually arrange these such that they're kind of like an IDE. So I've got one terminal that I edit in and another terminal that I run my code in. I've already set up a little scratch space here for us to work on our code. Okay, and I've also taken the liberty of going ahead and downloading the data set from the data distribution website that we're going to be using for this example. It says it's labeled as the Lecture 1 data set, but technically this is Lecture 3. But in the time of doing this remotely and online, lecture numbers don't line up anymore, so we're doing what we can. So anyway, first thing, let's unzip our data file. Okay, so there were two files inside of here, one called data.csv, and remember CSV is comma separated values, another called data_header.csv. If we look at what's inside of these guys, now the editor that I typically like to use is Emacs, but you can use whatever if you're wanting to operate from a terminal. But let's use Emacs to open up our header file. So the header file typically tells you a name associated with each of the columns in your CSV file. So in this case, we have a subject ID, we have a target, and we have a judgment. Turns out we're using a simplified version of a data set that I collected a few years ago and has actually been published. So cool stuff, real science. Now if we look at the actual data.csv, what we'll see are three columns separated by commas. The first one is our subject ID, the other one is our target that we're aiming for in the experiment, and the third is the judgment, where the person doing the experiment actually hit the target. Now, what we're talking about here, it doesn't really matter too much for the purposes of showing you how to plot stuff, but this was a study where people were judging the angle that things were turned. So the middle column, the target, is what the object was actually turned towards, the angle it was actually turned. And the judgment was where people thought it was turned to. Turns out people are really, really bad at judging orientations. But one of the cool things that, you'll learn in data science and is useful in things like, interface design is that it's okay for people to be bad at something as long as they're consistently bad. Because if someone is consistently bad at something, that means you can model their errors and fix them later. And turns out people are consistently bad at judging angles, as we're going to see when we plot this out. So let's go ahead and start by making a Python file called plot.py. So this is just an empty Python file right now, nothing there. So like with C, C++, Java, one of the first things you want to do is import the libraries that you're going to use. For our purposes, we're going to be plotting using matplotlib. And so we get that in here by doing import matplotlib.pyplot. Now this will let you access functions built into this library by typing, let's say there's a function called scatter for making a scatter plot. You can access that function by typing matplotlib.pyplot.scatter and give it a list of x values and a list of y values. Well, that's a handful. That's a lot. That's a lot to type. One of the nifty features of Python is you can give aliases to these really long library names. So you can do import matplotlib as, for instance, implot, something that's a lot shorter. So instead of typing all of this other stuff, we can just type implot.scatter. So let's go ahead and get rid of this and start going. So what's one of the first things you're going to need to do? When I'd ask this in class, people would say different things, and you can take your library. We got your libraries taken care of, this, that, and the other. And eventually someone will say, we need to open our data file. Seems obvious. That's the answer we're looking for. So using the example from our slides, we can use the easy bake example of opening a text file. So we're going to do data equal open, and then the name of the file we want to open. We want to open our data.csv file, and we want to open it for reading. So for those of you who are wondering, you can use this same function to open a file for writing or appending just by changing that R to a W for writing or an A for appending or whatever. But we're reading, so we're going to want to put an R there. So right now, data is a pointer to that file. What we want is data to be the actual data in the file. So we can read in the contents of that text file as one giant string by doing data equal data.read. But now we don't necessarily want everything as a giant string. We want to have it separated out by lines. So what we're going to need to do is split our data by the new line character. So now we can do data equal data.split and split by /n, the new line character. Okay, so remember the mantra, code test, code test, code test. Write a few lines of code and then test to make sure everything is working. So let's just print the contents of data at this point. So Python 3 plot.py. Okay, cool. So this is what this looks like as a list. So notice we've got, if we scroll up to the top, our list begins with a square bracket, the list ends with a square bracket, and here are each of our individual lines of the file, all separated out by a comma, and then the contents of each of these lines is inside of single quotes. So each of the lines still has columns of data in it that hasn't been separated out. So next thing we're going to need to do is separate out the individual columns of data per line. So again, pulling from our easy bake example, we can loop through the indices. So for index in range 0 to length of our data. Okay, so now let's actually get rid of this line and print data at index. And let's run that. Okay, cool. So now we're printing out the lines stored at each of these indices. So index 0 through however long our file is. Okay. Now what we want to do is split that by commas, because this is a comma-separated value file, a CSV. So what we'll need to do is we'll need to split data at index, because that's the line we're working with. So data at index equals data at index dot split. And we're going to be splitting by the comma character. So let's run that code and see what we get. Hey, look at that. Separated out by commas. We've got 3 columns worth of data. We've got our subject ID, our target, and our judgment. Okay, that's cool. But notice that these guys are all in quotes, which means they're all strings, and we can't do math with strings. Well, you can, but you're not going to get anything you want to see. So what we need to do now is we need to convert each of these strings, with the exception of our subject ID, because that's just a name. We need to convert the numeric values to something we can do math with. For the most part in this class, we're usually going to be working with floats. So let's get in the habit of converting these guys to floats. So remember, if we're going to access the first one of these, that's going to be index 0, the second is going to be index 1, the third is going to be index 2. So we want to start by converting index 1. Index 1 is our second value in this list right here, okay? And we can set that equal to float. Float is a function that's going to take that string and convert it to its floating point equivalent, so some fractional number. And so it's going to, instead of being the string 160, it's going to be the number 160. Okay, and we're going to want to repeat that process for index 2. Whoops. Okay, cool. Looks like it should work. Let's clear our screen and run our code. Boom. Oh my gosh! It broke! How unexpected! We've got an error here that says index error, list out of range. And here's the line of code that it's complaining about. It's complaining about line 10, which is us trying to convert subindex 2 to a float. Well, all of the lines in the file have 2 numerical components, index 1 and index 2. So why is it complaining? There should be one there. Let's debug things. So what we can do is we can move this print statement and put it before we do our conversion. And so print out the line of data that we're trying to convert before the program crashes. Let's see what we get. Let's clear our screen and run it again. And that looks, wait a second. Something is amiss. My goodness. That doesn't look right. It looks like there might be an error in the data file. To the data file. Let's have a look. So if we open up our data.csv, let's see what we find. Oh my goodness! Look at this. These columns happen to be separated by a space instead of a comma. It should be a comma like all these other nice, clean, perfectly constructed lines of data. My goodness, some inexperienced, roguish data entry person did not do his or her job or whatever and put spaces where there needed to be commas. Well, turns out in the real world, sometimes you're going to get data that's not properly formatted, and guess what? You have to fix it. Turns out this is an easy fix if someone does something as simple as accidentally using a space or a tab to delimit their data when they needed to use commas or something like that. So this is an easy fix for us. What we can do is we can fix this in our program by doing a character replace. We can search for and replace spaces with commas. The best place to do that is while your entire data set is still in the form of a string. And that is right after you do your data.read. So what you can do is you can do data equal data.replace and replace spaces with commas. And we can save that. Okay, so now let's clear our screen and run our program again. Hey, that looks good now. Nothing crashed, which is great. Okay, but now look, it'd be easy for us to accidentally deceive ourselves here, because if we look, it's like, oh my goodness, these things are still in quotes. That means they're still strings. Now look back at your source code and see where you have your print statement. Remember, we moved our print statement so that we could see what the data looked like before the conversion, so we'd know where it crashed. So if we want to see the data as it was converted, we want to put the print statement after our conversion. So let's clear it and run it. Oh, beautiful. Look at that. 3 columns of data. The first one's a string, the second one's a float, and the third one's a float. Beautiful. Okay. This is pretty much where we need to be. So let's plot this stuff up. Hold your horses. So in order to do a scatter plot, let's start with a scatter plot. That's the easy place to go. We would do mplot.scatter. Now the scatter function takes a list of x values and a list of y values. So remember from our slides, the x values or x-axis is going to be our what axis, or our category axis. And the y-axis are going to be our values, the thing that we're measuring, more or less. Or actually, the value that we have measured. And if we look here, what we want for x values is going to be that target column, because that was our ground truth. That's the thing, the what we're testing. And then the judgment is the thing that we measured, so the measurement at the what that we want to plot. So how do we get that out? Because right now, we've separated out our values, but it's still in one giant list called data. What we need is to have all of our x values in one list and all of our y values in another list. Well, one way to do that is to write another for loop and make a new list with our x values and our y values. But there's an easier way to do it that I encourage you to use. And Python has nifty list functions. One cool feature is called list zipping. So you can take multiple lists and zip them together into a single big list, but you can also take a big list, like what we have here, and unzip it into several individual lists. And that's exactly what we want to do. We want to take this list of all of our data and separate it out into a single list of subject IDs, a single list of x values, and a single list of y values. And the function to do this is, kind of makes sense, called zip. It'd actually make a lot more sense if it was called unzip, but there is no unzip function. To unzip your data, you put the variable name for the big list, and to unzip it, you put a star in front of it. So zip star big list name will unzip it into these columns here. So all of these S number whatevers will be in SID. All of the 160, 170, 180 whatevers will be in our Y, and then the responses that we measured are in the X. All the responses we measured will be in our Y list. Okay, so let's comment out this line for a second so we can debug. Actually, just do a little bit of testing, and let's print our SID column. Let's see what we get out. Hey, look at that. That is a nice, big, beautiful list of subject IDs. Now, one thing you might notice is that lists start with a square bracket and end with a square bracket. But this thing starts with a parentheses and ends with a parentheses. Ah, is it a list? And the answer is not really. This is what's called a tuple. A tuple is just like a list, except it's immutable. That's a fancy way of saying you can't edit it. So for most of the things we're going to do in this class, we're going to want to go ahead and convert what we unzip into a list. For the purpose of just plotting it, it doesn't actually matter. But I want you to get in the habit of converting these tuples to a list so you can edit them. So we do that by doing SID equal list, and it just converts that tuple into a list. Okay, so let's run our code and see what we get. Hey, there we go. A proper real list. Beautiful. Anyway, so let's go ahead and print out our other list just to make sure everything looks good, make sure that we haven't lost our sanity or anything. So yeah, this is all looking good. Print our Y values. Also all looking good. Beautiful. Okay, so the next thing that we need to do is, well, plot some stuff. Like I mentioned earlier, Matplotlib has a scatter function built into it. And so it needs you to put a list of x values and a list of y values, and it'll do a scatter plot of those corresponding x-y pairs. One of the important things is that when you go to plot your data, you need to make sure that the x values at index whatever in the x list correspond to the y values at that same index in the y list. So they need to be parallel lists, okay? For a lot of the data that I'm going to be giving you, that's going to be granted, so we don't have to worry about that too much. And honestly, most data sets you're going to get are going to be structured in such a way that's going to be the case. There are going to be a few exceptions, and we're gonna talk about those as we come to them. But this will get you through 80-90% of the things that you're going to need to do. Okay, so let's run this and see what we get. Well, I don't see a plot. I just see the output that we're normally getting. Weird. Well, maybe we just get rid of this and see what happens. Clear our screen. Nothing. Well, it didn't give us an error, so that's hard to debug, right? Ah, there's a gotcha here. So everything did work. Your program did exactly what you told it to do. The problem is that you didn't tell it to do enough. So it actually did make a scatter plot, but you didn't tell it you wanted to see it. So once you do your plotting, you have to tell Matplotlib that you want to show the plot. So after you do your scatter plot, your line plot, your bar plot, whatever, you have to always do mplot.show. Otherwise, you will never see it. So let's run it now. Boom! Well, look at that. That's a kind of pretty plot right there. I like that. I like it so much my Southern came out. Anyway, we talked about this, I think, in our in-person video lecture on like the first day of class. I am actually Southern, so you know, I ain't making fun of nobody. That's just the real stuff coming out. Anyway, moving right along. Okay, so that's actually a really nice looking plot right there. Now remember, I told you that there are certain things you have to do, otherwise I'm going to not accept your plots. And that is label your axes. Wow, that sounds so cumbersome. Yeah, it's really not, believe me. Okay, so if you want to label your axes, it's really easy. You just do mplot.xlabel and then give it a string of what you want to put there as the label. In this case, these were our targets in degrees. And so if we save that and we run it, there it is, targets in degrees. And not surprisingly, if you want to label your y-axis, it is mplot.ylabel. And we'll call this judgment. Judgment in degrees. Actually, I like to put these in parentheses because it's a unit. Matter of fact, don't even need n. That looks more nice, professional, and scientific. Just the unit in parentheses. Hey, there you go. Look at that. Ain't too shabby. All right. So that's looking pretty good. So, let's see. What would we want to do next? Perhaps one of the things we'd want to do is to do, I don't know. Let's get an average of the judgments at each of these positions. All right. So right now, how we've got this is we've got several individual samples at each of these positions, and people are noisy. Their responses are going to be noisy, so you're going to get spread in your data. But let's look at the average of each of these. So one of the things we can do to get this is we can make a dictionary, and we'll call this just DCT. So an empty dictionary. And we can make a list of all of the values and have that all of the values for a specific target, and have that as the value at a key in our dictionary. So let's try that. Let's see how that goes. So let's go for index in range 0 to length of our data. And what we can do is we can then add data at index subindex 1. So for each of our target orientations, we can append the judgment. So index at data at index subindex 2. Okay, so what we're going to do is build a dictionary where all of, let's bring up this up, all of our targets, our key values, and we're making a list of all of the judgments or responses at each of these orientation targets. So notice we've got 160, 160, 160, 160, a bunch of 160s, a bunch of 140s, a bunch of 120s, different orientations. And we have multiple measurements, multiple judgments and responses at each one of these. And if we want to get the average of those for each of the target orientations, we can make a list of each of those judgments and have it stored at a dictionary entry where the key is the target orientation. And this is one way to do it right here. So let's save this and run our program and see what happens. Oh my gosh, it broke! Key error. No negative 160. Well, we made our dictionary. Oh my goodness, but is there a key called negative 160 in our dictionary? And the answer is not yet. The answer isn't no, it's not yet. So the first time you try to add something to a list that's part of a dictionary, there's no list there for it to be added to. So you're going to have to make one. And this is where we can take advantage of try and except blocks. So what we can do is we can try to append something to a list at index or at key value, whatever. And if it fails, we can assume that the list at that key value doesn't exist yet. So what we can do is then use the exception to create a list at that location and initialize it to a list with the one element data index at subindex 2. Okay, so let's run that and see what we get. Okay, it didn't crash, which is good. That's what we want. So to make visualizing these things a little bit easier, let's just go ahead and comment out the part where we're plotting and just go back to looking at stuff from the terminal. Okay. So now what we can do is we can loop through each of the key value pairs in our dictionary. So for key comma value in our dictionary.items and print key, comma, value. And let's see what we get out. Okay, cool. So what we get is a key that is our target, and then a list of judgments associated with each of those. Now what we can do is we can construct a fresh X and Y value list, or lists, that we can plot. So what we can do is we can go ahead and make an empty X and empty Y, and this will overwrite this XY list that we built up here. Technically we don't need these anymore, but just for example's sake we're going to leave them here so you can reference this later. Okay, so now what we can do is we can construct a new list of X values, and our X values, again, remember that's our what axis, our category axis. And our what is going to be the orientation, the target at key. And the Y value associated with that is going to be the average of our values. Oh goodness. Well, we get the list of values, but we don't have an average of them. Well, what we can do is we can import another very useful library. Up here at the top we can do import numpy as np. And numpy is a numerical processing library. It can do some really cool math, in short. We're going to use it for some kind of boring math right now. We can do np.mean and our list of judgments associated with that key value, and that'll give us the average, the mean average of the values for that target orientation. So let's just go ahead and print these out. Let's print out our last X value and our last Y value on those lists, and see what we get. Oops, we left in this print statement here, so let's get rid of that one and actually have a look at, there we go. Okay, so now what we have is our target followed by the average of the judgments for that target. Target, average of the judgments for that target. All the way on down from negative 160 all the way up to positive 180. So, kind of cool, kind of cool. Let's plot this instead now. And we can just uncomment our code for plotting. Uh-oh. Wasn't getting capturing my keyboard for a second. Okay, cool. Now that's neat. That looks pretty cool. Okay, so now that we've got our averaging of these points worked out, and we can do a good scatter plot. Let's look at that again. Yeah, looking good, looking good. Let's plot this a different way. Instead of us doing a scatter plot, let's do a line plot. So the function for doing a scatter plot was mplot.scatter, right? So naturally, the function we would need to call to do a line plot would be, say it with me now, mplot.line. And if you guessed that, you would be wrong. What it is actually just mplot.plot. So if you want to do a line plot, just changing scatter to plot, and still it takes an X value and a Y value as input, or X list and Y list. We can run that, and now we have a line plot. And the cool thing is we can actually combine scatter plots and line plots. So if we wanted to do the line plot but also include the individual points from our scatter plot, we can just do mplot.scatterxy and mplot.plotxy. And we can run that. We'll get something that looks like this. Kind of cool, right? Okay, so these are the basics of doing line plots and scatter plots using Python and matplotlib. It's a pretty easy plotting mechanism. The most complicated part of this whole set of examples we went over was this part here. We did the averaging. Um, if this part was a little bit challenging for you, especially for those of you who might have less experience doing this kind of stuff, don't worry too much about it. But you need to practice it. So practice doing this stuff here and try to work out like why, say, the try and except work, or why we're making the X and Y lists. And if you got questions about it, talk to me, talk to. I'm actually trying to avoid using specific names for our wonderful class TA in case I have to recycle this one later, like next semester. But for the purpose of this semester, if you need to talk to me or Riley, in future semesters, if you need to talk to me or whoever our TA happens to be, this is, don't hesitate to do that. We're happy to talk to you about it. Because, we've all been there. We've all had to learn something new for the first time. But yeah, pretty much everything else here should be fairly straightforward. A lot of this came straight out of the easy bake solutions that we talked about earlier. So if you have any questions about this, please let me know. A better version of this code is actually at the tail end of your slides. So I've actually worked through several different common plot types we're going to be using in class. And so you can go and reference these. You can copy and paste these and practice them. Do whatever you need to. So we've got examples for doing line plots, examples for doing scatter plots, bar charts on top of bar charts, and combining scatter plots and line plots. So anyway, folks, I hope you're all doing well, staying happy, healthy, and safe. And if you have any questions or need help in the meantime, please let me or TA know. And I will see you guys in cyberspace. Take care.